Welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we're in AP Chemistry talking about really periodicity, periodic trends. And so it's just a little bit more than honors. So y'all can fill in the blanks as we go along. So you should know some of this already from honors. Dmitri Mendeleev, Henry Moseley, and Glenn Seaborg discovered or developed what? Who told the elements where to go?
Mendeleev.
Okay, so what did he do? How did he tell them where to go?
He found the mass.
He found the periodic table, right? Now, so this guy, I had not heard of him before, but they talk about him in your book, that he really figured it out at the same time as Mendeleev. Because remember, Mendeleev did not invent the periodic table. He didn't invent the patterns that are in the elements. They've always been there. But he discovered it. Well, that guy did it at the same time. But Dmitri was doing it to write a chemistry textbook, and he got it published. So he's the one who made it famous. And he, remember he was telling people you're going to discover an element, and this is what its properties are going to be. And then there was a guy who discovered an element and tested the properties, and he said, wait, you did it wrong. Go back and retest it. It's got to fit in this square on my periodic table. And Mendeleev was right, the guy was wrong. So it was pretty sensational. It was like he was psychic. And so he really defended it. He argued with other scientists about it, and so he kind of gets the credit. The other guy figured it out at the same time. They said they've never heard of him. He got to be more adamant about your idea being right. Okay, effective nuclear charge. So this is, when you learned this in honors, you learned about electron affinity, ionization energy, atomic radius. You learned about these trends, but we really didn't talk about so much effective nuclear charge. But it is that there are forces of attraction and repulsion in an atom. So the electrons are attracted to the nucleus. So it's one of the things. The other one, we called it shielding effect in honors. Your book says that it is screened. They called shielding effect screening. It just means that electrons get in the way between the nucleus and the electron, and it makes it where the nucleus has less power or influence on those electrons. There's all those little negative electrons making charge, and it's sort of lessening the attraction, okay? Electrons are also repulsed by each other. So there's that energy going on too. I thought it was funny, your book used the word repulsed. I'm like, wow, that's getting strong. I wanted to have said that they are repelled. They said repulsed. It's got a little more emotion to it. I don't like you. Okay, so the effective nuclear charge has a symbol. It's Z sub F, EFF. And the electron experiences a net attraction that, as a result of the nuclear attraction, decreased by the electron repulsion. So it's just all of these forces added up. Being attracted to the nucleus, other electrons in the way, disliking other electrons, it all ends up as ZF. Okay, now there's the actual nuclear charge, which is the number of electrons, and that's just Z. And there's also how much the screening is happening. It's called the screening constant, and it is S. And it's close to the number of core electrons. So if you count out the core electrons, not the valence ones, take those off, it'll give you a number. So here is an example, sodium. And so if we want to know the core electrons, we should look at its noble gas configuration. So the noble gas before it is neon. So we would put that neon in square brackets. And I like to put my little 10 down there, but that's neon. But it looks like a 16, but that's a 10. And then after that is 3s1, right? Everybody good with that? So it's got it's the same as neon plus one more. So it's Z is 11, minus 10 is core. So it's ZF is plus 1. Okay, now in reality, it's not +1. Remember how it says it's close to the number of core electrons? In reality, it's 2.5. And the reason why is it has to do with not only these forces, but it's how close it is to the nucleus. If an electron is closer to the nucleus, it's going to have more nuclear force on it. If it's further out in the atom, it's going to have less nuclear force. And that's why the numbers are a little bit different. Okay? See, that was new. Y'all didn't learn that in honors, did you? It's nice learning something new. Okay, the effect of nuclear charge on the periodic table increases from left to right. I guess I'll write out right here. It increases left to right as you go across a period. So the effect of nuclear charge increases only slightly down the column. Yes, sir.
What does it say in this parentheses right there? Does it say 2.5 plus something?
That it's real. That's what it really is. It's really 2.5. And remember, you can get close to the right number by just counting the number of core electrons, but it's really going to be slightly different depending on how close or far it is from the nucleus. So that can change a little bit.
How do you find the real number?
The real number, I don't know.
Oh.
They must do it experimentally or something. Maybe it says in the book. Maybe it said it and I didn't know. Okay. All right, periodicity. So if you remember from honors, but some of y'all didn't get this wonderful experience in honors because you didn't have me, I read you this book. Does anybody remember why I read you this book? Well,
Family about the splitting parents?
yes, there was something about parents, but that had something to do with it, but there was something else. This is the People in My Family book. Do we need to read it again? I think we do. All right. The People in My Family. Oh, I have 5 people in my family. And there's not a one of them I'd swap. There's a sister and 2 brothers, a mother and a pop. That's me. 5 is such a lovely number. I'm so glad that I've got 5 people in my family. 1, 2, 3, 4, 5. And we have some foreshadowing here, like all great literature, about the coming conflict. Okay. Now I've got 5 monsters in my family. And we have lots of fun. Furry wife, scary husband. Fuzzy daughters, hairy son. 5 is such a scary number. Oh, I'm so glad that I have 5 monsters in my family. 1, 2, 3, 4, 5. This is the climax. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now this is the denouement. Did you learn that in literature? That's the unfolding of the resolution. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, if you were learning to count, these are the correct questions, but we're not. We're learning about the periodic table. And what we learned was the families, the columns, have similar members. So the monsters look more like monsters than they look like the Muppets. The Muppets will look more like each other than they do like the monsters. Okay, everybody got that? But also, the families have similar members. If you look at the 2 dads, they're the biggest. They have the biggest nose. They have the biggest eyebrows. If you look at the smallest member of the family, they're pink, and they're the smallest. So the periodic table is the same. The columns, the families are alike. The noble gases are alike. The halogens are alike. The alkali metals are alike. But they also have somewhat similar members. If you look at the tops of most columns, a lot of them are so small that they're gas. The smallest one is gas. If you look at the bottom of the columns, the most of them are so big they're radioactive. So there's a little bit of similarity in the periods also, not just the columns. Do you see that? But they're more like their family than they are like the representative member. And that is the chemistry idea of periodicity. But it's much easier if you have your book. Okay, so people in my family, that's what the mom is over there. The moms both had red curly hair. Okay, the columns or families, periodicity, oh, it's right there, are more like each other than periods rows that have similar members. Okay? Now, what we're about to learn are these trends, and it's easy to remember if you just think about what the elements want, what everybody wants. And the first thing they all want is to feel like a noble gas. They want a full valence shell with full electrons. And this is called the octet rule. The octet rule, they want 8 valence electrons, everybody except hydrogen and helium because they're too little. Everybody else wants 8 valence electrons. And the guy who figured this out, he said there are certain trends in nature. For example, the math behind a snail shell and a spiral galaxy is extremely complex. I think you don't learn it here at East until pre-calculus. Sometimes you learn it in Algebra 2, but it's extremely complex. And it's the same math behind these two structures. Is there anything in common with the two, a galaxy and a snail? No. But there are patterns in nature seen all over the universe. So the guy who thought this up, he said that there is something about the number 8 in chemistry, like music. And you know, music is based on physics. Those of you who have had physics, you know about the frequency and the nodes and the standing waves. Remember all of that from physics? And how music is based on math. And music is based on this octet. And so he said, there's something in chemistry that's based on the octet. And everybody said, you're stupid. That is a dumb idea. There is nothing in common between the elements in music. Guess what? He died, never got to see his idea become famous. And then after he died, they went, you know what? That fellow was right. So if you're, believing in your idea, believe it. Remember, Bohr is the one who said that electrons can have 2 natures, and Einstein told him he was stupid. But Bohr was right. So, if you're right, believe in it and hang on to it. Okay, periodic trends. So if we know what all the elements want, and if we can think of them, it's just sort of an analogy that works really well, that if we think of our electrons like children, our electrons are children, and we're going to think about what happens to them. Okay, so alkaline metals and alkaline earth metals are bad parents, and they do not want their valence electrons. They want to get rid of them. They want to look. So these are our parents who are putting their children up for adoption. Okay, so alkaline metals, the ones over by the kitty cats, and alkali earth metals want to lose electrons. On the other side, and then they're going to feel like a noble gas. On the other side of the periodic table, the halogens, oxygens family, nitrogens family, they want to gain electrons, and then they can feel like a noble gas. So these are like the people who adopt the children. They want more children. Okay, non-metals, that's like the ones near carbon, the ones we skipped there, they're like divorced parents who work out sharing agreements. That's why we've got a little divorce there. Some of y'all have divorced parents who have sharing agreements with you, right? So that is where we get our covalent bonds, is when they share those electrons instead of transfer them. Now metals are different. So notice when we do our oxidation charges, we go 1, 2, 3, skip, -3, -2, -1, zip, and we just skip that whole D block transition metals, right? This is why. Metals are hippies. That's why we got our P symbol here. And they let their electron children run free and wild. Whoops, I'm getting my sleeve too close. Free and wild. Okay, so there was an idea in the 60s that they felt like all the problems they had were because their parents were too strict in the 50s, these baby boomers, and they thought that it would be better if people were communists, they lived in communes, they shared all things, including spouses, or they didn't bother with marriage but with partners, and they felt like the best way to raise children was to just let them run free and wild, no rules. Let them, dirty hippie children running around everywhere. They lived in these communes, and you heard this idea idolized in some of the song lyrics. There's a song called Seattle, and it says, growing up like a child, beautiful, free, and wild. See, people in the 50s wouldn't think it was a good idea to have a beautiful, free, and wild child. They'd want a child that said yes ma'am, no ma'am, and paid attention to the rules. But there was just this idea to let them run free and wild. You also hear it in the song Born Free, free as the wind blows, and stuff like that. All that ended, anybody remember what killed it? Charles Manson. He was in charge of one of these hippie communes, but he wanted revolution to bring about global change, build back better, and so things weren't happening fast enough. So he decided that there needed to be chaos so that things could be rebuilt, so the whole world could be a hippie commune. And so he thought the way to do that was to have a race war. And so he got his followers to kill a bunch of people and make it look like it was racially motivated. It wasn't. The killers were white. The killees were white. Everybody was white. And then they all got caught and went to jail. And it really horrified the nation. And that was the end of the hippie commune. But before that, it was a popular idea. Okay? So what happens, this has to do with chemistry, as metals do exactly the same thing. They do not assign their electrons to a particular atom. They share the electrons. They let them run free and wild. They can just go from one nucleus to another uninhibited. And it gives them their characteristics. It makes them shiny. It makes them good conductors of heat and electricity. And all those properties of metals you learned in honors is because of this. That they just let their electrons go wherever they want. Okay, no rules if you're an electron for a metal. Okay, so if you keep those ideas in mind, there are 4 fancy ways to say this, not talking about children and hippies. Okay, and it's called electronegativity, ionization energy, shielding effect, and element size. All are related to this. So what is electronegativity? The ability to attract electrons to oneself. How attractive are you to electrons? Ionization energy is the energy it takes to remove an electron. Shielding effect, we already talked about, they called it screening effect in your book, is the power of the nucleus is blocked, can be blocked by electrons. Okay. And the atomic radius, the size of an atom, as you go across a period, the size decreases. Now, all of that you learned in honors. Now, we're going to draw it on the on here. So we're going to draw these trends here. So the first one is going to be the pink one, electronegativity. Put the number 1 over here. And as you go down a column, it decreases. Okay? And as you go across a period, it increases. Okay? Next, we're going to do, we'll make it blue. We'll do ionization energy. Okay? Number 2. So as you go down a family, ionization energy decreases. As you go across a period, ionization energy increases. Okay. For number 3, shielding effect, we'll make it orange. Orange is a good color. Okay. Shielding effect, as you go down a column, it increases. As you go across a period, there is no change. Stays about constant. Okay? And then the last one, element size. We'll do it green. Doop. Okay, as you go down, it increases. That makes sense. As you go down. But as you go across, and this is the weird one, it decreases. And it's because all of these make sense if you think about what they want. Electronegativity, the ability to attract electrons to itself. As you're going down, they're getting more and more electrons. They can't keep up with them. It's harder to attract one. As you go across, these guys want to lose their electrons. These want to keep theirs and steal yours. So as you go across, their ability to attract electrons increases. Yes? What was your question, Titus?
Oh, sorry. I just got confused because you had all the arrows going the same way. Sorry.
Yes, it's what happens as you go down and what happens as you go over. Okay, so ionization energy, the energy it takes to remove an electron. Well, as you go down, they have more electrons, it's easier to remove one. As you go across, it gets harder and harder to remove one because they want to keep theirs and steal yours. Okay? Number 3, the shielding effect. The more kids you have, the less likely you're going to have much influence over them. They're going to start influencing each other. So the more you go down, the shielding effect increases. But as you go across, there's no change because they're starting to hold their electrons tighter and tighter, and the nucleus can still have power over those electrons. And then the last one, element size, it makes sense that they get bigger as you go down, but as you go across, it actually gets smaller. Even though there's more electrons and the nucleus is bigger, more protons, more neutrons, more of everything, but as you go across, they want to keep their electrons and steal yours, so they're holding them tighter and tighter and tighter. Now that, you learned all of that in honors. We're going to add to that, but everybody good? Remember that from honors? Okay. All right, so let's move right along then. Okay, number 3, sizes. So just a little bit more about sizes. Remember I said we're going to add to it? Here it goes. So bonding atomic radius. First of all, how do you know how to measure the radius of an atom? They do it by halving the bond distance. So it's half the bond distance. Now, trends in ionic radius. Here we go. Okay, so now we're not talking about atoms anymore, we're talking about ions. Okay, so everybody get that in your head. Now it's ions. So cations, over there by the kitty cats, are they going to gain electrons or lose them? They're going to lose. So when they lose electrons, are they going to get bigger or smaller? Smaller. They're going to get smaller. So cations are smaller than their parent atoms. They lose electrons. Anions, do they gain or lose? So therefore they get bigger. Yes, y'all are brilliant.
Thank you.
They're going to get bigger. Now, for ions with the same charge, okay, so what do I mean about that? I'll show you down here. Ionic radius increases as we move down a column in the periodic table. So, they all have the same charge, and so we're looking at an ion of lithium and an ion of sodium. They have the same charge. They're both +1, but sodium's just bigger. So the radius is going to increase as we go down the column. That's all logical, right? Okay. So there's another thing, though, called isoelectric series. And this is fun because this is new and this is AP level. Okay. So if you think about it, this group all have the same number of electrons. How can that be? Well, let's look at it. So look at oxygen. Okay, if it becomes an ion, it's going to get 2 electrons and have 10, right? Fluorine, if it becomes an ion, it's going to get 1 electron and it's going to be 10. Sodium, if it becomes an ion, it's going to lose 1 and it's going to be, yes, you guessed it, 10. And magnesium, if it becomes an ion, it's going to lose 2 and it will have 10 electrons. And aluminum is going to lose 3 to have 10 if it becomes an ion. Everybody see how all of these have 10 electrons? Yes? Okay? So this is the trend. As atomic numbers increase, the ion radius, and this is shocking, decreases. Decreases. And the reason why is the nucleus pulls more on the electrons. So what's different about these is not the number of electrons, it's how many protons it has. So the one of these that's going to be the smallest is which one? Who's the smallest? Who has the least protons? It's oxygen. See how oxygen is number 8? So oxygen has the least protons, so it's not going to be able to pull very much. It's going to be big or small? Big. It's the opposite. So which one is the smallest?
The biggest.
The biggest, which is? Aluminum. So aluminum is the smallest and oxygen is the biggest. As the atomic numbers increase, the radius decreases.
So basically, why do they all have 10? Like,
Because they've all gained or lost electrons when they became an ion to be like neon. They all want to be noble guesses when they grow up.
Wait.
It goes back to our octet rule. They all want to be the noble guess, or at least feel like it.
why does aluminum want to be neon? Is it because it's closer to neon than it is to argon? Is that why?
It's because that family, the boron family, when they are just by themselves, monatomic, they lose electrons to become an ion. They are the +3 family. Boron's family is the +3 family. That's why there's that green little +3 that I wrote on my periodic table up top. Okay, we're processing that. All right, so now let's see if we can apply it. Which is bigger, calcium atom or calcium +2 ion? Calcium atom, because it hasn't lost 2 electrons. Which is bigger, bromine atom or bromine ion? Bromine ion, because it gained 1. Which is bigger, sodium or fluorine? Fluorine. They're the same, but fluorine has less protons, so therefore the electrons can spread out a little bit more. They're not being as attracted to that nucleus. Yes?
You said as atomic number increases, electrons decrease?
As atomic number increases, electrons increase. Because if it's a neutral atom, protons and electrons are the same. Okay? Everybody good? All right, moving right along. Ionization energy. So we're going to talk about each of these little ideas a little bit more in depth. Ionization energy is if you took electron is ionized, if it's moved out and they say to infinity, it's so gone that it has no effect anymore on this atom. So that's it being ionized. So ionization energy is not just one thing. It breaks down into which electron you're taking off. If you're taking off your first electron off of an atom, it's called the first ionization energy, I1. And it's the energy to remove the, yes, you guessed it, first electron from the neutral atom. And by definition, in gas phase. So here we have sodium. We took off an electron, and now it's that ion. The second ionization energy is the energy to remove the second electron from a neutral atom in gas phase. So now you've got your sodium ion, and you're going to take off another one. Which one do you think is going to take more energy? That first one or the second one? Why? You're right. Why?
Because
How many doesn't want to lose? One. It's not going to be happy about you taking another one, because it was all happy. It was feeling like it was neon. And now you're going to make it feel like fluorine? Nobody wants to be fluorine. You see the problem? So that's going to take a lot of energy. Okay? So it takes a lot more energy to remove an electron from an inner shell, not valence. And that's what that second one was for sodium. Okay, another thing has to do with this is that the S and P block elements show a larger range of ionization energy values than do the transmission, I could say a transition, not transmission, metals, okay? So the why is it harder to take an electron out of an S or P than it does a D? What are those transitions? They're hippies, so do they care if you take one of their kids? Have one, have two. If he wants to go with you, then he is free to go. He's his own little person and can make his own decisions, okay? So the reason why is that metals are hippies. So we'll just draw a little peace symbol there. Metals are being hippies there. That's why you can get their electrons real easy. They're just letting them go, be light. They're letting them just be shiny, whatever they want. Okay, smaller atoms. Would it be easier to take an electron, do you think, from lithium or cesium? Who's going to be harder to get their electron? Which one's going to be harder to get? Is it easier to kidnap a kid from a family of 7 kids or 1 kid? 7, right? So these are our kids, and they're kind of going to get lost. So smaller atoms have higher ionization energies. Okay? Because it's harder to get them from a small one than from a big one. Okay? If you have increased effective nuclear charge or decrease, if you increase the effective nuclear charge or decrease the distance between the nucleus and the electron, it increases the ionization energy. So to increase the energy needed to take off an electron, what would do that is having a higher effective nuclear charge or having them closer to the nucleus also makes them harder to get. Okay, so that's just sort of following some of these ideas and applying them. Now there are some exceptions, of course there are. Okay? The ionization energy is less for boron, everybody look at the periodic table and think about this, than it is for beryllium. Okay? And so why is it easier to take boron's atom than beryllium's when boron is closer to the noble gases? Can anybody think of a reason why? Yes.
Boron has more electrons.
It has what?
More electrons.
Kinda. They're on the, what?
Does beryllium not want to go to helium, and so it's closer to helium than boron is to neon?
No.
No.
No, it's where they are. Okay, everybody imagine the electron configuration for beryllium. Okay, it's got a full 2s level. But boron has one little electron all by itself in a p room, stuck out on the very edge of the atom. Do you see how easy it is to get that one? It's just hanging out there ready to get snatched. So the ionization energy for boron is less than beryllium because that one electron alone in the higher energy level, p orbital, is easier to pick off.
Ms. Blackburn?
Yes.
So it's like the further it is from the nucleus, the easier it is.
Yes, absolutely. And that's because of that screening or shielding too. Okay, also, the ionization energy is less for oxygen than nitrogen. Okay, so everybody look at that. Oxygen instead of nitrogen. Think about that. Okay, why is it easier to take oxygens than nitrogen? What is the electron configuration for nitrogen? 1s2, 2s2, 2p3, right? Everybody see that? Each one of those electrons have their own nice room. You see that? But with oxygen, Hund's rule, somebody's got to double up. those two electrons are both negative being shoved into one orbital. What do likes do? Attract or repel? Repel. So it's actually easier to get that other electron out of that room because they're already repelling. They're already fighting. They're already not getting along. One of them's out of there. Do you see that? And you can also think of it. Remember when I told you that they like full or half full better than a mishmash? And really it's going back to that again. Nitrogen is more comfortable with its half full p orbital than oxygen with its mishmash. Do you follow that one? Okay. So, and therefore easier to pick off. Easier to pick off. Okay, electron configurations of ions. When electrons are lost from an atom and it becomes an ion, they come off from the orbital with the highest principal quantum number. Remember that's lowercase n because it's outermost. Yes?
Can you draw like the
The electron configuration for nitrogen, is that the one we want here? Okay, so nitrogen, we'll put him right there. He's number 7. We'll give him a 7. Is 1s2, 2s2, 2p3. Which if it was in little boxes, you'd have an S box. Sometimes they do them as an X. Another S box, and then 3 P's, which only get 1. But if it was oxygen, let's change colors. We'll add blue. So oxygen is the same. Oxygen is 8, 1s2, 2s2, 2p4, and instead it's got one more electron right there. They don't like each other. They're both negative. They're pushing against each other. It's easy for that one to just pop right out of there. Okay, did that help? Little pictures there. All right. So this is the thing. We learned the order they fill. Okay, so if we wanted to do sodium, if we wanted to do scandium, 21, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Okay, now, this is just hypothetical. I don't know if it does something weird. So, instead of if an electron is lost, it's not the 3d10 one that's lost. But when it becomes an ion, it doesn't just lose electrons in the order they're filled in. Instead, it loses from the highest level. So for that one, it would lose one from 4s, not 3d, because 4 is bigger than 3. And the reason why it has to do with this is because it has to do with the nucleus. The nucleus is pulling on these. That 3D is a little closer to the nucleus than that 4S is, and so it's going to hold on to it tighter. We good with that idea? Okay, so it's not just exactly reversed. Now, if there are two different filled orbitals on the same level, they go in order of the L quantum number. Remember that one is written in cursive. It's your chance to whip out your cursive and draw a little cursive L, okay? And remember, so they will go in order of F, then D, then P, then S. 3, 2, 1, 0 in order of that. Okay, so it goes in order of S, P, D, and F. Feel all right about that? Losing electrons? Let's talk about gaining electrons, okay? They fill the next orbital with the highest N value. And this is what we talked about yesterday in our warm-up. For example, fluorine is 1s2, 2s2, 2p, and it's 5. But when it becomes an ion, it's 6. That it just goes right in that very next one. So it does fill more in the order of the period of our electron configurations. Is that a question?
Yes.
Is it because I wrote messy? That's a P, not an R.
I know. But I had a question about like the electron like,
Yes.
where it's like shaped like a triangle and do the lines, right?
No, don't do that. No. Use the periodic table. Don't do that. Here, I'm going to do it on a little periodic table so you can follow it. People get those lines off and then they miss every single problem. The periodic table, the reason why it has the shape it does is it tells you the order. So this is the S block. See how there's an S written over these two over there? This is the D block. This is the P block. And this is the F block. You just go left to right and it tells you the order. So if we wanted to, so the only difference is the levels go 1, 2, 3, 4, 5, 6, 7 here. But here they start with 3. Scandium is 3, not 4. See my little red 3 I wrote on my periodic table? So this is 3, 4, 5, 6. And down here at the bottom, this is level 4, 5. So the periodic table tells you. So if I were to do gold, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, then it goes down here to 4f14, then it comes back up here to 5d 1, 2, 3, 4, 5, 6, 7, 8, 9. 5d9. And I was able to do that just going back and forth on the periodic table. So you need to learn how to do that. Don't draw those arrows because they don't exactly fit diagonal. You have to do it twice and then start. So that's where everybody gets confused and they mess up. Don't do it. I can show you how to do it more. We can practice. All right, next. All ionization energies are positive because energy must be absorbed to remove an electron. So remember how exothermic is negative, endothermic is positive? It's positive because electrons must be absorbed to remove an electron. That makes sense? Everybody good still? Okay. Electron affinity. Affinity means to like. If I have affinity to chocolate, I like chocolate. Electron affinity is the energy released when an electron is gained by an atom. And it is a negative number. Okay, so that energy, the greater the atom is attracted to the electron, the more negative the affinity number. So those over like those halogens are going to have high numbers. Noble gases do not want electrons, and how they show it is they make the number positive. They so don't want it that it's the opposite of wanting it, which is negative, it's positive. Okay? Next idea. Periodic trends in electron affinity. In general, electron affinity becomes more negative, that's like higher, it likes this electron more, as you move to the right and up on the periodic table. So there's some exceptions, of course. Noble gases, they don't want electrons. Also, alkali earth metals don't want an electron to stick by itself in a p orbital. So alkali earth metals don't want an electron to stick by itself in a p orbital. So so instead of going up, getting more negative as you go across, it doesn't. Okay, so think about that. You can sort of imagine it there. Nitrogen's family don't want electrons to have to share an orbital, so they are not wanting an electron that much either. They like full or half full better. They like full or half full better. So as you do some problems, you'll apply this, it'll make more sense. Okay, metals, nonmetals, and metalloids. Metal characteristics. Okay. Metallic character is how much an atom exhibits the properties of metals. And in general, metals are shiny, they conduct heat and electricity. They're ductile, which means you can make them into wires. They're malleable, which means you can make them into foil, into sheets. They're solids at room temperature, mostly melt at high temperatures, just not hydrogen. We're going to talk about hydrogen later. And they have low ionization energies. They form ionic compounds with nonmetals. They often can form more than one cation. So let's talk about tin. Tin can be tin 2 or tin 4, good buddy. Okay? Now, we can think about why that is. Okay, let's look at. So tin 2, to become tin 2, is it going to gain or lose electrons? Lose. Okay, so everybody look at 10 on the periodic table. Which 2 electrons is it going to lose? Which ones are they going to lose? What orbital are they in?
P orbital.
P. It's those 2 in the P. Because remember, they like full or empty. They don't like mishmash. So 10's like, I'm going to become an ion. I'm losing these 2. And then I'll have a nice full empty P orbital and I'll be happy. You see that? So this one loses the 2 P's. Okay? So now what about tin 4? He's already lost the 2 P's. Who's he going to lose now?
D.
The 2 what?
The 2s one.
The 2 S's. He's getting rid of those. Remember, they're going to lose the level first, and those S's are on level 5. Those D's are on level 4, so we're keeping those. But we're going to lose both of those on level 5, so it's going to lose 2 P's and 2 S's. We'll make it like that, 2 S's. So now you understand some of this better, don't you? What you learned in honors, you've got to learn why a little bit. Okay, oxides are compounds formed with oxygen. Very important.
Miss Blackburn.
Yes.
The idea is that it doesn't want like a charge, it just wants to be the ion.
Tin can be found uncombined in nature. I think it can do either one. Some of these metals can be metallic, or they can become an ion. They're versatile.
Okay.
They can do different things.
But like, how do we know if it wants to keep it versus if it doesn't?
Usually by looking at what it's bonding to.
Okay.
You look at the compound and see if it's stannic fluoride, tin fluoride in your toothpaste. We know from the name that it's an ionic compound. It was formed with the ion.
Okay.
Okay. Okay, so metal oxides. Where are we? Am I in my notes? Oh, when you have a metal oxide, a metal formed of oxygen, they're basic, not acidic. They're basic. They dissolve in water to make metal hydroxide. So, for example, if you put sodium oxide in water, it makes sodium hydroxide, and you know sodium hydroxide is a base. If they are insoluble in water, they still react with acids to make a salt in water, and that's on the bottom of your metal activity series. Remember that certain ones can react with water, others have to react with an acid. Okay? Nonmetals. General properties of nonmetals. They can be solid, liquid, or gas. They're not shiny. They do not conduct heat and electricity well. They have a lower melting point. They're not malleable, not ductile. Some are hard like diamonds and some are soft like sulfur. So, they have a lot. They tend to gain electrons. Whoops, gotta get my arm out of the way. They tend to gain electrons when they react with the metals. Okay? Compounds made entirely of nonmetals tend to be molecular substances, meaning they are covalently bonded. And non-metal oxides are acidic. Okay, so for example, carbon dioxide, non-metal, with water makes carbonic acid, soda pop, Coca-Cola. There's your fizz in your Coke right there. Metalloids, okay, they're in between. They're a little bit like metals, a little like not. An example is silicon. Silicon pure doesn't conduct electricity, but you can put stuff in its crystal. It's called doping it, and then it conducts better. You can change what you doped it with and change how much it conducts electricity. And that's what the whole idea of making computers is based on, is changing how much it conducts electricity. Okay? Next, alkaline metals. Okay? Okay, so we're going to talk about a few of the families. Alkaline metals are the same as other metals, but they're not hard, they're soft. They have a low density, they can float in water. Low melting points, they're very reactive, they don't exist uncombined in nature. They react with water, making a hydrogen gas and metal oxide or hydroxide. This is a very exothermic reaction, they get hot, and they're so reactive they are banned in Paulding County. I used to buy them in Cobb County, I don't know if they banned it since then, and I caught the school on fire one time. Only once. So what I did is I had some sodium, and I put it in water, and what it normally does is it goes psss, and it's a metal floating on water, so that's cool, reacting, fizzing, making white smoke, and on a really good day it'd go poof, and it'd catch on fire, and it'd make a really pretty pastel yellow and blue and pink flame. So pretty, such a great little reaction. And then it makes it a basic solution. So then I add phenolphthalein, and I got a hot pink color. It was just a good demonstration. One day, I'd done this, hundreds of times. One day I'm doing it, I put it in there, and it just went kaboom and blew up and caught the ceiling on fire. But luckily, they wisely put flame retardant ceiling tiles in the chemistry lab, so it burned itself out after making a hole about that big. So all's well that ends well. So then I came here, and sodium is banned here, but I found a bunch in that stockroom when I came here, and I thought, well, I got to get rid of it. I could call, the hazmat people to take it, or I could just take the kids outside where it's safe and there's nothing I can catch on fire, and I could show it to them, and that, because it just turns it into salt water at the end, I can neutralize it'll make sodium hydroxide, I neutralize it, there's nothing harmful in it, it just can explode. So before I did, like a good teacher, I went out, I took it out my back door to test it, and I put a piece in. It went off like a bomb. Kapow! And it was so loud in that little courtyard, I lost my hearing a couple of days. So then I was like, oh no, we cannot show this to children. They'll be losing their hearing. So I gave it all to Mr. Myrick, and he has a farm, and he rigged up a contraption where he could be far away from it and dump it to have it blow up. He was all excited. He had it dump in an old potty. He was going to blow up the potty. It was going to be like a YouTube moment. So he had his long thing, and he dumped it in, and it did nothing. He was so disappointed. So it did not blow up his potty at all. It did not react good at all. Okay, so that is our alkaline metals. Hydrogen can react with alkaline metals as the hydride ion, which is not H plus, it's H minus. Remember how hydrogen can act positive or negative? That's when it acts negative. Alkali earth metals, they're the second column. They're same as the alkali metals, just less. They're less soft. They're slightly higher, but still a low density and melting point. They're still very reactive, but less, a little less. They don't exist uncombined in nature. They still react with water, making hydrogen gas and metal oxide or hydroxides, and it's still an exothermic reaction, but it's not banned in Paulding County, so we get to burn magnesium and put calcium in water and all that. Okay? Now, trends for selected nonmetals. Hydrogen. We're going to talk just a little bit more about hydrogen. Okay? So there are things that make it like a metal and like a nonmetal. It can lose an electron and become, that should be H plus, that was a typo, H equals, to become like an alkali metal. It can react with nonmetals like a metal. Okay? But it's a diatomic gas, and that is not very metallic, is it? No. It has an extremely high ionization energy, like a nonmetal. It's got an electron, it doesn't want, it likes it. It can gain an electron like a nonmetal. It's not totally opposed to getting another electron. And it can form covalent compounds with nonmetals like a nonmetal. So what do you think it is classified as a metal or non-metal? It is classified, I won't keep you in suspense anymore,
Non-metal.
as a non-metal. So it's a non-metal over there in the metal family, which is kind of funny. It's an alkali, metal, non-metal. And I didn't know that until I read the book. I just heard, well, it's kind of weird. I never knew that it was officially classified as a non-metal. Oxygen. Okay, so do you remember what allotropes are? Wait, I sometimes do a lab called allotropes of sulfur. I might have done it with y'all. It smells really, really, really bad like a poot. You go home smelling with your hair will smell like a poot. So sometimes I just don't have it in me to do it. It's a great lab, but it's that sulfur could make all different forms and it's still sulfur. Diamond could be graphite, it could be soot, it can be a diamond, right? So, so carbon has different allotropes. Well, oxygen has two allotropes. It could be O2 or O3, the oxygen we breathe, and ozone. You all know about ozone, okay? Oxygen attracts electrons from other chemicals, so therefore it is called an oxidizer. So that's something about it. And then a little bit more about halogens. Halogens can be solid, liquid, or gas. They're diatomic. Remember, they're part of our 7 diatomic molecules. They're used for disinfectants. They're very reactive. Whatever you put them in, they get out of. So you know how in Jurassic Park they say nature finds a way because the dinosaurs just keep coming back and eating you? Well, as chemists we joke, halogens find a way. They get out of anything you put them in. And so even those little blocks I showed y'all that had the chemicals in it, the halogen was getting out. The iodine was. They're highly negative electron affinities. Some are deadly. I think all of them can be deadly if there's too much. Noble gases are monatomic, meaning they are not diatomic. That helium floats around just as a helium atom. Neon floats around just as a neon atom. Okay, they're not reactive and they're gases. We used to say they're inert, but now we can make them react if we do unnatural things to them. Okay, so that is these notes. These are pretty easy, right? Okay, the book work is already on Canvas for you to start working on. Like, share, subscribe. Science is great.